So continuing with the lecture on chapter 3, let's recap quickly. Um, right, a set is just a collection of objects, again called elements. Um, an element is either in a set or it's not in a set, and the elements are in no particular order. This means X is an element of A. This means X is not an element of A. Okay, we had a couple examples of that. Right, all of these sets are the same. This set is the same as this set because all I did was mix around the presentation of the elements. And this set is still the same as that set because elements, even though they're listed more than once, they're still just in the set once. They're not in the set multiple times. There is a concept of sets where elements are in there multiple times. It's called a multi-set, which is something important in combinatorics and in number theory, but we're not doing that. Sets can contain anything as elements. Letters, numbers, shapes, people, sports heroes, or whatever. In particular, it can also include other sets. So this was a set with 5 elements, 1, 2, 3, 4, 5. But this 5th element is actually a set itself, which has 3 elements. But the elements of this set are not elements of the larger set. It's the set itself that's an element of the larger set. So, like for example, 3 is an element of this set. 5 is not an element of this set. 5 is an element of that set, but it's not an element of this set. This thing, the set containing 2, 5, and pi, is an element of this set of 5 elements. And that brings us to Russell's paradox. When you ask, what about a set? Can a set be an element of itself? And when you do that, it leads to this paradox, which is called Russell's paradox, which is similar to the, that setup with the barber in town. Right? There's a barber in town. In this town, this barber, he's the only one, and he shaves anyone who doesn't shave himself. So the question is, what does the barber do? Does he shave himself or does he not? And if the barber shaves himself, then he can't shave himself because he only shaves people who don't shave themselves. If he doesn't shave himself, but then he has to shave himself because he shaves people who don't shave themselves. So we're left with these contradictions, which you can't determine whether the barber shaves himself or he doesn't. In Russell's paradox, A is the set of all sets X, for which X is an element of X. B is the set of all sets X, for which X is not an element of X. And then if B is an element of itself, then by the definition of B itself, B can't be an element of itself. Right? If you say B is an element of itself, but the elements of B are the things that aren't elements of themselves, the sets that aren't elements of themselves, so that can't be right. If B is an element of itself, we contradict ourselves. B is not an element of itself. If B is not an element of itself, then by definition, B must be an element of itself. So again, we contradict ourselves. A proposition can't be both true and false at the same time. So this is known as a paradox or an inconsistency, and that's the problem with naive set theory. There are others. This is probably the simplest one. It's just a neat exercise to think about right now. Kind of get your mind twisted up in knots a little bit. But essentially nobody cares about them. We just avoid them. There is a way to get around it. It's called axiomatic set theories or Mello-Frankel set theory or whatever it is, but it's really complicated, that stuff. And that has rules. It has certain specific axioms that are set up. And you can only use those axioms. All right. And then we had set builder notation. And set builder notation looks like this. This is the set of all x such that p of x is true. Sometimes instead of the line, people write a colon. This is more like used in typeset and in handwriting. This is used more often. And then sometimes given a known set A, you'll see the following. The set of all elements x in A such that p of x is true. So that creates a subset of the set A. And then we had some known sets, the natural numbers, integers, positive integers. And then the rational numbers has to be defined using set builder notation. It's the set of all A over B, such that A is an integer, B is an integer, and B is not 0. So a set of all fractions of integers. And in this presentation of the rational numbers, right, you see the same rational number listed differently, listed many times over in different ways, but it's still the same number. And then some numbers that aren't rational numbers, like pi and e and square roots of non-perfect squares. And then we have a couple of examples there. Okay. So now, we had more, didn't we? Yeah, subsets. This means A is a subset of B. This means A is a proper subset of B. So A is a subset of B and A is not equal to B. And sometimes people write this to mean proper subset. This guy means the empty set. The set with no elements in it. And then we had the order or cardinality of a set. Okay, so now let's think about this for a moment. Power set. Given a set A, let the power set of A be equal to the set of all B such that B is a subset of A. So it's the set of all subsets of A. Okay, P of A is called the power set of A. All right, how about this? Let's do the power set of the set 1, 2, 3, 4. So it's the set of all subsets of the set with 1, 2, 3, 4. So start with sets of order 0. Sets of order 0, subsets of order 0. What's the only subset of order 0? Right, order was the number of elements in the set. So a subset here is going to have order 1, 0, 1, 2, 3, or 4. Right, because this has got 4 elements in it. So what's the subset with 0 elements in it? Every set has this thing as a subset. The first one is the empty set. And that's always a subset. And then we've got the subsets with just one element in them. So the subset with the set with just 1 in it, the set with just 2 in it, the set with just 3 in it, and the set with just 4 in it. Subsets with 2 elements, those would be what? One, 2. Next. 1, 3. 1, 4. 2, 3. 2, 4. 3, 4. And then subsets with 3 elements in them. 1, 2, 3. 1, 2, 4. 1, 3, 4, 1, 2, 4, or 2, 3, 4. And then subsets of order 4, which is just the whole thing. All right, so if you want, you might want to think of these as having different colors. Like that. Right, so subset of cardinality 0, subsets of cardinality 1, there's 4 of them. Subsets of cardinality 2, there's 6 of them. All right, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. Subsets of cardinality 3, the subset with 4 removed, the subset with 3 removed, the subset with 2 removed, and the subset with 1 removed. 4 of those, and then the whole thing. All right, how many do we have there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 has what significance with regard to 4?
4 squared.
2 to the 4th. Yeah, it's 4 squared, but 2 to the 4th is actually the way we want to think about it. But we'll talk more about that later. Okay. All right, guys. That's all for today. So keep an eye on your email tomorrow. Okay, and then we'll we'll have announcements and stuff there. Okay. All right, everyone. Have a good afternoon.